Good afternoon, everyone. All right. So the benefits of being last is I get to use little pieces of everybody else's presentations that went before me, so I'll try to make some references as I go through. So my title is High Performance Technologies for an Analog-Centric World. And you've probably heard this today, and I'm going to make sure you hear it a few more times. The world is analog. Okay? But let me continue, and we'll talk a little bit about how the world is analog and how it relates. Okay, so I'm going to first try to cover analog in our world today, just to show you some real live examples of how analog impacts your life every day. Then we'll talk about the diverse technology needs. Analog is very diversified. It's very fractured, and so you have to meet the analog market with lots of different technologies. And then we'll talk about some of those technologies. Then we'll cover some of the obstacles, the challenges in moving analog forward, scaling, kind of Moore's law for analog. And then finally a few conclusions. So, I've got two big questions, okay? The first one is, the world is going digital, right? I mean, we hear it all the time. Everything digital this, digital that. So you would think that the world is digital. So I guess the second big question is, then why am I up here talking about analog? Okay? So let's cover some of those. I'll try to answer those for you. Let's look at a few smartphones. Okay, everybody here probably is very familiar, may even have an iPhone 4 or a Samsung Galaxy. Okay, they're very popular smartphones in today's market. So why don't we crack one of them open and see what's inside the thing? So we tried to do that on an iPhone. And you can see over on the right-hand side, this is a teardown of what an Apple iPhone 4 looks like. And you can see all the different chips here. The red ones correspond to logic, the blue ones to analog. What you notice is, yes, you have the big apps processor. That's usually an A4 or A5 or whatever maybe out of Samsung. Gets a lot of publicity. You've got the NAND flash, NOR flash, and there's a quad baseband in here as well. So you've got four major chips that are in there that relate to the logic or the memory, but you've got 9 different chips, maybe more, that relate to the analog and power. You've got the power, so the thing turns on. You've got audio, if you want to listen to your headphones, listen to the music. Video, display, the touch screen, accelerometers. There's a lot of chips in here, and those are mainly analog, and they go around the much more publicized logic and memory chips, but they are what helps make the iPhone and the Galaxy have the features you like. Maybe some of the features you don't like. So let's take a look at a notebook. Okay, let's closer look at a notebook. If you didn't have analog, the thing would not turn on. And if it did turn on, the screen wouldn't display. Well, there's a whole lot of other functions that wouldn't work in case turning on or displaying were not already big enough problems. So, if you look closely at the every computer, pretty much, you see the Intel inside. So maybe we need to put a big analog inside marker now to get some recognition for our analog efforts. So this is then, if we go here, this is another look. Analog is everywhere. You have it in wind farms, for offshore power systems, cell phones, power over Ethernet that we talked about earlier. TVs, industrial applications, medical, baseband stations. If you've got a camera, you've got analog inside. Your car has tons of analog in it. and just a host of other white goods, printers, so forth. So almost everything you touch in your world today has got analog inside of it. It has the logic and memory in there too, but the analog generally is what gives it its character, its personality. So, coming back to the two big questions. Okay, the world is going digital, right? So the answer is yeah, the world is going digital. We see more and more digital in our world today. So then why am I talking analog? Because the world's going digital. But it needs analog to get there. So many of you are probably saying, huh? What's he talking about? Why does digital need analog to get there? And the reason is that we live in the real world. Right? The real world, as one of our earlier speakers showed, is composed of things like temperature, pressures, weights, position, motion, sounds, light, video. These are things that are analog in nature. And that's what the world is. That's what we have around us right now. Right? But the question is, how do you electronically interact with these external analog things, and how do you control them? How do we try to control, as much as we can, what goes on in the real world? Right? So you wind up with what's often called a signal path. You sample things from the real world, perhaps through sensors or other analog devices. Then you go through signal conditioning. This generally is an amplifier, maybe a converter, to convert that analog signal into ones and zeros, and then that feeds into the processor or the DSP. The processor makes some decision and then tries to feed an output back to the real world, but that also has to go through signal conditioning. Again, maybe a D to A converter, and then an amplifier to basically turn a knob or increase the light or the sound, what have you. So this is how the real world interacts to digital engines. Okay? So generally what you see is the processor is the high buzz, okay, the high publicity. Intel with their I-cores or the latest the latest A4 or A5 processor. So these are the things that get a lot of attention because they're very exciting. They're the leading edge process technology. But these things, these signal conditioning, these are the what I call the low buzz stuff that actually makes the whole thing work. Okay? And that's the analog stuff. So as one of our speakers said, for every processor you may have 6 to 8 analog chips that go here. Okay? A sensor, an amplifier, a converter, an amplifier, and a converter, and usually in the middle controlling the power for all these things is a power management chip. So as I like to say, if the world's going digital, please buy more digital because we sell 7 or 8 analog chips for every processor going out the door. So it's kind of a good deal for the analog guys too. So I'll try to boil this into a golf analogy, okay? So you hear a lot of buzz, the buzz about logic, the buzz about memory. So there's an old golf analogy says that you drive for show, and I'll kind of put logic and memory in there, and you putt for dough, okay? So we'll let the logic guys and the memory guys drive for show, but the analog guys, our job is to clean up when the day is done for the dough. So that's a good deal. All right, so let's talk about some of the diverse needs in the analog market. So if you look at the application space in analog, generally you have 2 major classes, really. There's analog CMOS technology, and then there's power technology. And again, some of our speakers earlier have talked about some of those. If you're in the analog space, you may be having sensors, baseband chips, power management chips, audio amplifiers, data converters. These can be general purpose and also high performance. In the power space, you're looking at, again, automotive applications, maybe anti-braking systems, engine controls. You have LED drivers and lighting, Class D audio, solar applications now becoming very strong, motor drivers, telecom, the power over Ethernet that was mentioned earlier. So these are all there, and there's so many more applications that I could list, but there are a diverse set of analog requirements in today's world. But these are very fractured. They're not just one technology. And to illustrate how diverse analog is, I wanted to just pick on one parameter, the voltage level. Let's just look at the voltage levels between digital and analog. Well, here's digital, okay? About 1.2 volts, 1 volt, 1.5 volts, somewhere in that neighborhood. Very nice, very stable, you know, depending upon what technology, that's what you have. You can tell by this chart that there's probably some other things that I'm going to put on here, and that's because analog is diverse. So, if you're into energy harvesting, you may be looking at circuits and applications that have to handle devices that have to work at 10 millivolts. If you're in audio signals, you may be in 100 millivolt range. If you're in cell phones, power management, and precision analog, maybe you're in the 5 volt space. Okay, if you move further, hard disk drives or in some industrial applications, and other power management can be in the 16 to 24 volt range. If you're automotive, LED drivers, solar, you might be in the 60 volt range. If you need to do telecom or power over Ethernet, now you need 85 volt capability in your technology. If you want to do industrial applications or solid state lighting, like replacing these lights with solid state LED, you're up maybe at 700 volts. And then finally, if you're doing electric vehicles, or maybe you're doing offshore power transmission, you may be at 1200 volts or more. Okay? So not one technology clearly can do all that, but that is the wide range that analog tries to handle. So there are many, many, many different processes that you have to have in your portfolio if you're going to be an analog player. So how do you build an analog portfolio? Okay, so to do that, you clearly need a very good base, a very good foundation for your technology. And so we've chosen here to start with an analog CMOS platform. And this would include, have logic CMOS, analog devices, passive resistors and capacitors, and bipolar for band gap references, things like that. And so that becomes your technology building block, if you will. And so then you layer additional things and capabilities on top of that. So the next thing you might choose to do is high voltage and power. So here you need very, very higher voltage devices. Drain extended CMOS, where you take advantage of drift regions and lighter doped materials to increase the breakdown voltage of devices. And then a favorite for most power guys is a lateral DMOS transistor, a double diffuse device that has very good switching capabilities. Very low on resistance when it's turned on, and very high blocking voltage when it's supposed to be off. So a very ideal switch. And then if you're going to be a player in power, you need not just good silicon, but you need good metal. Because when you're pushing amps across your chip, IR drops in your metal can be very important. So then, moving up, you might want to have high performance. So an analog CMOS process that you use for a wireless cell phone application may need to be very, very cost effective, because the bill of materials is always under pressure in those kind of applications. But if you're trying to build very, very high-end data converters, as our previous speaker was trying to do, there you want to worry about really trying to build the very best components possible. Lowest noise, thin film resistors, very good poly-to-poly capacitors. And so these are technologies that you layer on top. You take the base process and you add these features then onto it. Next, you need memory. If you're looking at technologies today, 0.18 micron and beyond, you're really looking at system on a chip. They may not be the type of intense integration that you might see at 32 nanometers, certainly not that many gates. But you're bringing power, you're bringing precision, you're bringing logic together, and often that requires memory, either non-volatile or SRAM, and so you need to have that capability then as one of your building blocks, if you will, on your technology. And then finally, you need to have IP, analog IP, as well as ESD. One of the main reasons chips don't go to market on time is still ESD. It was that way 15 years ago, and it's probably still that way if you ask a lot of the customers today. It's always a challenge, and certainly as we try to raise the voltage levels and that, and the higher and higher, ESD is always an ultimate challenge. So this is an example of how you might structure an analog portfolio if you want to be a player in the analog industry. So with that in mind, what I'd like to do is then try to show you some of the things that we've done along that same line, those building blocks, to show you what 동부하이텍 has been up to in the last few years, and it's been quite a lot actually. Going back to our slide here from before, this kind of shows you again the different technology careabouts. Again, on analog CMOS and power, sensors, baseband chips, PMICs, audio, different types of amplifiers, different types of converters. In the power space, again, engine and analog braking systems, LED drivers, Class D audio, motor drivers, power over Ethernet, a variety of things. So now if you look at what's behind that, those are the applications, but what makes those applications possible? What from a technology standpoint? So in the analog CMOS space, these are the types of things that you would need in your toolbox to be able to go off and do world-class or very competitive designs. Certainly, you need logic CMOS. That's always a given. You're going to integrate logic functions on board. Analog CMOS, you need devices that have a focus on noise, have a focus on matching, that can operate at higher voltages for long periods of time, not just switching as logic devices would. Generally, you would have poly resistors, but in extreme cases, you might use thin film resistors for the very best in class applications or products. Again, poly-to-poly capacitors or MIM, metal-to-metal capacitors. Different choices, each has different benefits and drawbacks. I'll talk a little bit about that later. Drain extended CMOS. Many times you have a 5-volt circuit that needs to touch a 20-volt battery charger, let's say. So do you build a 20-volt technology, or do you find a way to build a cheap, no-cost 20-volt device in a 5-volt technology? So often that's what we try to do, is realize some higher voltage so you can do a little bit more with your technology than just the nominal voltage ratings. Generally, The world certainly has moved a lot more to CMOS, but bipolar is still a very important component for many applications, particularly for building stable band gap references, things of that type. So you generally need an NPN, sometimes a PNP. JFETs. These are not very common devices in the foundry world, but if you're into analog guys know what JFETs are. JFETs are usually very low noise type of devices, so they can be very useful. So analog, people worry about low noise, low 1/f noise. They worry about low temperature coefficients. These are things that are very important that can take, if you have these low, if you have good capabilities in here, can turn a good product into a great product. Low capacitor voltage coefficient and also low capacitor dielectric absorption. This has a lot to do with how the plates, the poly-to-poly plates are doped, and also what kind of material you use for the capacitor dielectric and how you deposit it. Component matching is always critical. You want low package shifts. If you get great performance on the probe station, you don't want to lose it putting it in a package. So you need to have means to keep that those shifts 0 or low. And here you really want to focus on performance and density. Now if we flip it and look to power, then the name of the game generally is BCD, bipolar, CMOS, and DMOS. Here you want logic CMOS, analog CMOS, LDMOS, lateral DMOS transistors. These are, again, are power switches. The workhorse is the N-channel device, but also often customers use P devices as well. Drain extended devices, as before, polyresistors, MIM caps, the same type of components, except now you have very high and varying voltage range. 30-volt devices for a lot of PMIC, power management chips in cell phones and so forth. 60 volts into automotive, 85 power over Ethernet, 150 volts, 700 volts for solid state lighting. Often you need very thick copper metallization for low resistance power. Again, ESD is always a challenge at these kind of voltages. And again, if you're in the power space, you focus on power and you focus on voltage. So these are the things that are behind the types of products that go out into the market. Dongbu has a wide variety of technologies, both in the 0.35 micron space and in the 0.18 micron space. Analog CMOS processes, shown in green, and more BCD power devices, shown in blue. And so you can see, again, 3 and 5 volt analog CMOS, 5 volt analog CMOS, and then a wide variety, 24 volts, 60 volts, 85 volts, 60 volts, 30 volts, 20, 85 volts, and again the 700 volts as well. So again, all of these different plateau regions on that one earlier chart for voltage we try to cover. At 0.18 micron, which is really where most of the analog and power community is going now, we've tried to build what we call a modular platform. These are really 5 processes, all connected, all related to one another. An AN180, which is our core process, analog CMOS, and then with module additions, we can build the BD180LV, which is a 30-volt process using EPI, or a BD180LV no EPI, it's 20 volts. The very high performance HP180, which is based on precision, and then a 60-volt process, BD180X. This is my 3rd time at this Analog Leaders Forum. 3 years ago, I sat here and I kind of drew the outline of this, and it was only a dream. Okay? Today I can stand here and say that every one of these now exists. They've all been released over the past year and a half or so, and thanks to a lot of hard work from process development folks, technical engineering, manufacturing, and the marketing team, we now have, this is reality. So it's nice to be able to talk about something real rather than what you're going to have. So what I'm going to do is just kind of give you a very high level, one slide snapshot on each of these. I'll run through these pretty quickly. But AN180 is a 0.18 micron analog CMOS, and it's the workhorse process. It's 1.8 volt and 5 volt CMOS. You often need isolated transistors to decouple noise from the substrate into the sensitive analog. A lot of times you need low VT transistors for more headroom on your designs. Low 1/F noise. Noise used to be like the last thing we measured, just so we could write something down and send out the the design manual. Now it's like the first thing we measure because we have targets and something to shoot for. Then if you look, you can do quite a bit of logic here, 115,000 gates. So really you can start to, at 0.18 micron, you can start to realize really system on a chip with a lot of capability, maybe several 100,000 gates of logic. You can do some damage with that kind of capability. Drain extended devices. So again, if you need to touch some higher voltage, you can do so. Bipolar is there for band gap. A lot of resistors, good capacitor. This is a metal-to-metal cap, 2 femtofarad per square micron. Often you need different types of non-volatile memory. You need to trim something. You might have multi-time programming, which is an E-squared PROM, or you might have an anti-fuse or an EPROM for one-time programmability. But non-volatile is becoming a real trend in the industry, and it's very important for analog. Often designers use it for post-package trim, but now with more systems you can see many other functionality coming on board that needs analog trim. Just just to prove that we have them, drain extended devices. Now if you move to power, now you're talking about a BCD technology. This is BD180LV, and this is the EPI process. This is 30 volts, and it really is focused on power. And this is exactly AN180, the one I showed before. We just add modules to get 30 volt power. So all the component set is essentially the same with the addition of the power devices here. This is just some example of safe operating area. You have to make sure your power device doesn't blow up. Blowing up power devices is not a good thing on a chip. So we try to make sure that doesn't happen. But the key parameter for power usually is specific on resistance. And so we benchmark against some very, very stout competitors, TI, ST Micro, Toshiba, and we've done pretty well. This process is extremely aggressive, and right now, from the literature data, it's the lowest on resistance in the industry. So for any voltage you choose, the idea is the lower on the y-axis you are, the smaller the area. Okay, and that's the idea. You want a smaller chip, so you get more die per wafer. You lower your die cost. So you want smaller. You want lower specific on resistance. So everyone tries to, if you could, you'd be down here. Physics says you need to be somewhere up here, but lower is better. So that was 30 volts. If you move to 60 volts, same kind of idea. BD180X aimed at 60 volts. Same exact process. It's modular. We just move out the 30 volts, bring in the 60 volts. And this is actually our second generation process. We had the one in red was BD180. That was released about 3 years ago. But our goal for BD180X second generation was the dark blue. And the light blue says we're better than it here and maybe a little worse, but almost right on top of our targets. And just for reference point, the green down here shows BD180LV. So still, having a optimized low voltage process is always better. You can get lower die size here, but this process is very, very, very good. 60 volt process, and we're pushing it even further. This is some preliminary data focused on 85 volt capability, just again showing safe operating area that these devices are breaking down and maintaining in excess of 85 volts. So this is what you need for power over Ethernet type applications. Then you go to precision. So precision, the goal is do everything you can to make the components as close to perfect as possible. And so we took AN180 and we just tried to make it better. We made the noise reduce. We played tricks to get noise down, both on the NMOS and the PMOS. We introduced thin film resistors, cychrome resistors, with much better temperature coefficients than this actually. JFETs. Okay? I like to say that most people in the foundry can't even spell JFET, but you know, we're really focused on building JFETs. Very, very good performance capacitors as well. And I'll show you a little bit more on that. Here's an example of thin film resistor. This is temperature coefficient. So this is the amount of change in parts per million per degree C. So you want a resistor, the ideal is a resistor that never changes. But resistors change with temperature. What you'd like is a resistor that just changes very, very little. And so this does that. And then a capacitor, you'd like a capacitor where the capacitance doesn't change with voltage. Well, this is about as low as you can get, and this is with poly to poly. So very, very good performance capabilities. And then if you move in the other direction, 700 volt capability. So again, you know, we can make them small voltage, we can make them large. So what I wanted to do in the last section here is just talk about some of the challenges that you have in analog technology and driving the roadmap. Some of them are technical, and some of them are economic. This is a look at Moore's Law. Okay, so Moore's Law is the scaling. This is like the the mantra of the logic world. And for digital, you know, if you look back in the 70s and so when modern CMOS started, we've been on a path that generally every generation the feature size shrinks to about 70%. So you get double the transistor density. Okay, so you can just see it just marches on. 32 nanometer in this year. You know, maybe have to move to EUV lithography next year, but this will continue until maybe somewhere out in 2020, and who knows. So that's what digital looks like. Now, just a little example of how Moore's Law works, okay? Maybe everybody here knows, but just a little example. Let's say we have a chip and the whole thing is digital. Right? So it's 100% logic. Blue is logic. So I put a little scorecard down here. So our first generation, we've got a chip. We'll say it's 100%. We'll normalize everything. The die per wafer we say is 1. This is normalized. The cost is 1. The cost per die is 1. Now what happens when we go to second generation? Everything shrinks, just a 70% shrink. Right? So now if I look at the scorecard, it says that the area per die is 50%. We just made the chip half the size. So we get twice the number of die per wafer. Now the key is that the cost to build that wafer maybe goes up maybe 40%. If it goes up more than 2, it doesn't make sense. The economics are bad. But generally from one technology node to the next, maybe it's a 40% increase on wafer price. So the point is that our cost per die is now just 70% of what it was. That's a good thing, right? Everything went down 30%. So if we continue this, it's cheaper, we go the rest of the way, and you know, it just gets cheaper all the way down. That's what makes the digital world turn. Okay, that's it right there on that chart. Now, what happens for analog? Okay, well, first of all, there ain't a lot to scale. Okay, if you look at the digital, if you've got an SoC, the digital will scale very nicely. Analog will scale a little bit, and power doesn't scale much at all. In fact, sometimes power goes the other direction because maybe instead of 40 volts, they want 60 volts now. So, and now if you just look at maybe what a typical analog IC might look like, you might have half of the chip is high voltage and power, and that's not shrinking. The digital, yep, that's going to shrink great, but I don't have much of it. And the analog, well, it's kind of medium. So if you try to now look at the same kind of scaling as we did before, now you got to look at three pieces. Your chip is made up of maybe 20% digital, 30% analog, and 50% power. Now, every chip isn't like this. So if you have a different chip, you would look at different scaling. Here's my scorecard. Okay, I start out, I'm normalized. Now, how does this scale? Well, the digital is going to scale just like digital does. It's going to scale 70%. The analog, maybe 85%, okay? And power, I'm being generous. I'm saying 90%. So it means it shrinks, you get 10% improvement or 15%. Okay. Now, how does my scorecard look? Well, I'm now only 73% area per die. On digital, I was 50, but now I'm 73. So I get 37% more die per wafer. But if the cost per wafer is 40% higher, I got a more expensive chip, right? And that is the big problem with analog and analog scaling. Okay? If you continue that, the situation doesn't get any better. Okay? So a couple of things. One is we need to figure out how to make analog or power scale better. Another thing is you might argue that in analog we don't use the most advanced fabs, so maybe this 1.4 is a little bit too much. Okay? But the point I want to make is logic behaves nicely with Moore's law, analog not so much. So basically you need the Z direction for analog. We talked earlier about how FinFETs were going to become important for logic. Analog has a similar kind of need. We have a number of factors that impact density. STI, chemical mechanical polishing, forces density rules. Well dopings are getting too heavy, so that reduces our drain extended devices. Copper back end of line, we get dishing problems. So if you really look at how we're going to drive more improvement in our analog, it's not just going to be through scaling. Scaling is it isn't going to get there for analog. You got to do more. We've got to move in the Z direction. So LDMOS may need to move towards trench style devices, so you can use the Z direction to get rid of the drift region that is in the X and Y direction, put it in the Z direction where it doesn't take up space. Isolation, again, high voltage means large spacings. Trench can help there. Capacitors, okay, use MIM caps over active areas, okay, reuse space. Resistors, okay, polyresistors consume space because they sit down next to transistors. If we could work out a low-cost thin film resistor and put resistors above active area, again, we reuse space. So analog scaling is going to be a mixture of Moore's law. And here's kind of what's happened. Analog follows behind logic. It does scale. It has scaled. It's important that it scales. But really, as we start to move beyond 130 nanometer, you just don't get much return for your buck, particularly if you're in higher voltage areas. So we're going to continue to do scaling, but it'll slow down, and we will have to do more along the way of component scaling and how to reduce white space on our die. So, a few conclusions. Okay, the real world is analog, okay? We love the digital guys, but the world we live in is analog. And that's good news for us because we're analog guys in this room. So, so the world is not going to go away. Analog is what gives products their character. They may have a very high buzz engine inside of them, but generally analog is what gives them the features that we like. But analog means diversity. Okay? But diversity is a good thing, because I once asked somebody, I said, boy, it would really be nice if there was an ITRS roadmap for analog. And I came to the conclusion, it's really a good thing there's not an ITRS roadmap for analog, because that way, if you use your head, you can get to something faster than the other guy. Okay? Once you put it on a roadmap, everybody shoots for that. Okay? So it's actually a really good thing that analog doesn't have a roadmap, a published one. Okay, as I said, analog scaling more challenging than digital, and you're going to have to do more than just turn the knob on the photo machine, because you're actually going to have to try to figure out how to build stuff in the new direction. I tried to show that we've spent a lot of time working on analog, and we've developed what I think are some very high-end leadership technologies in that future. And really, from the final thing is, from 동부하이텍 standpoint, our vision, we're not there yet, but we're working to reach our vision, which is the most respected analog foundry. So with that, I'd like to thank you for your attention. Thank you.